Okay, now we go to example 9, and then we'll take a speaker in the shape of a circular plate, and we say the speaker has a radius of 6 over pi again, right? That's the total radius of the speaker, and it also has a power of 100 watts. What would be the sound intensity heard 3 meters away, right? So in order to do that, we have to take a ring that makes up that plate, right? And then integrate over all of those rings. So we're gonna say, imagine this, the blue one that I drew here, imagine that you have a ring here with a radius of r prime, like this, r prime, and then you have here 3 meters, and you have here r, right? So then how can we apply the general equation that we derived for the sound intensity of a ring? Remember we said that the sound intensity of a ring, di, is equal to dp over 4 pi r squared. And then when we integrated this, we ended up getting I is equal to p over 4 pi r squared. And it ended up being not an integral. So this is the r squared right here. So it just was basically 3 squared plus r prime squared, right? So it's going to be p over 4 pi. And we could do a general equation here. This is an x, so we can say x squared plus r prime squared, right? And then we can put the 3 meters in later on. This is going to be the sound intensity of a ring, but in our case, this is going to be dp, right? The power of this is going to be dp. So it's going to be di is equal to dp over 4 pi s squared plus r prime squared. Then we have to integrate over all of those rings. So I have to find the relationship between the power of just one ring and then the radius r prime, right? So we can define something known as surface sound density, sigma. Sigma is going to be the dp over dA. This is again similar to how we do this for electric fields and for electric potential. So we say here dp is the power of that divided by the dA represents the area of this, dA. So it's going to be dp, and then what is dA? dA is going to be 2 pi r prime dr prime, right? Basically 2 pi times that radius r prime, right? And then the thickness of that r prime. So you're taking the circumference of that circle and then multiplying it by its thickness. That gives you its area. So then, right? And then what is the limits of your integral? From 0 to the radius of the ring, right? And then you can kind of take out some stuff. So again, the 2 pi comes out, and over divide that by 4 pi, and sigma, if it is a uniform speaker and all portions of the speaker are as loud, therefore that means the sigma is uniform, the sigma will come out of the integral also. So then you just have 0 to r. Now we can put in the numbers. The r is the 6 over the pi, right? And then you have here r prime dr prime divided by, and then the x was 3 meters, right? So that's 3 squared is 9 plus r prime squared. And then we can actually calculate that. So the 2 pi over the 4 pi just becomes 1 over 2, right? And then 2, 1.7011997 times 10 to the minus 1. Now, what's the surface sound intensity? Well, sigma is going to equal, as uniform, then this becomes sigma A is equal to P. So sigma is just equal to P over the A, right? So similar to when we did the linear sound intensity, lambda is equal to P over L when it is uniform, right? Then when the sigma is uniform, it's just equal to the P over the total area, right? So then it's just going to be P over 2, and then the total area is pi r squared. Right, and then multiply by that number, whatever that number was. So what is the P? The P is 100 divided by 2 pi minus 1 watts per meter squared, right? Then we can convert that to decibels. So multiply by 10 to the power 12. .7 decibels. Okay, does the answer make sense? The other one, when it was a ring, what was the answer for the ring? When it was just a ring and it was 100 watts, this was around 118, almost 118, right? It was 117.99. So now this is louder, 118.7 decibels. So does that make sense? Well, it should make sense because now the speaker is completely filled in. So basically you are closer to portions of the speaker. So if it was a ring, you're farther away from the edges of the ring. So you're farther away from the music basically, right? But if the music is filled completely as like a circle, then you are closer to the different portions of that speaker, right? And therefore it should be louder, and then the answer does come out to be louder, 118.7 decibels. Now we'll see what happens if the surface sound intensity is non-uniform and it changes as a function of the radius, okay? And then we'll see how that affects the answer. Thank you very much.